Okay, so thank you very much for coming to this AMET session. It's a pleasure to have Benjamin Bernat with us. So he's at Taiwan National University. Is that the name?
National Taiwan.
National Taiwan University, and he's going to talk about continuous time stochastic games with imperfect public monitoring. Bernat, you have 1 hour, and then we'll leave 10 minutes for questions and comments. Okay, the floor is yours.
Thank you very much, JC, and thanks a lot for inviting me to present in your seminar. It's great to get to meet everybody here and to get a chance to present my research. So when most of us think of dynamic games, the first thing that comes to our mind are repeated games, sort of the simplest environment that we can think of in which we can model dynamic interactions. And the players just repeat the same stage game over and over again. And despite the simple framework, we can already get some interesting equilibrium behavior because we can provide non-trivial intertemporal incentives to the players by conditioning future play on past actions. Now, an inherent limitation of repeated games is that it will always model an interaction in a static environment. The simplest way to extend this from a static environment to a dynamic environment is to look at stochastic games. So now in each period, instead of playing the same stage game, the players play the same set of games. And which game they play exactly in each period depends on a stochastic state variable whose distribution is affected by the player's past actions. Now, so in this way, we can get an environment that reacts to the player's actions. And the players have to take into account not only how or what response their actions will trigger from their opponents, but also what future opportunities their actions will create. So as an example, we could consider an oligopoly with inventory levels where each firm's inventory levels is the stochastic state. And in this case, the state is chosen directly by the players, and the inventory levels will determine the nature of the competition in the next period. Another example would be a competition with research and development. As an example, let's say Apple and Samsung try to develop new features to attract new customers and get them to move away from their current provider to a new one. And so if a new feature or a new technology is developed, then this will change the nature of the environment. So first, if this new technology can be patented, then it will change the research environment forever because nobody else can now patent the same research. And then the nature of the competition will also change because for a few years, that company will have some edge over their competitors. Now, stochastic games have been used to study many other dynamic interactions, such as regime change games, common resource management, or strategic experimentation, and many more. Now, in this paper, I will focus on games with observable states and unobservable actions. And when I say unobservable actions, I mean imperfectly observable through a public signal. Now, in the literature on stochastic games, there are two types of stochastic games that have predominantly been studied. So the first one is what I would call an irreducible game. And this is a game where the underlying state process is an irreducible Markov chain. So that means that from any state of the game, any other state of the game can be reached with positive probability. So the oligopoly would be such an example. Maybe a regime change game would be such an example. But the competition with research and development would not be such an example because we can't go back to a state where a technology has not been developed yet, once the technology is developed. Now, for these types of games, the characterization usually relies on a convergence to a steady state distribution. And we can get that convergence by looking at the limit as players get arbitrarily patient. So as players evaluate their payoff stream infinitely far into the future, it does not matter anymore at which state they started, because eventually the distribution over states will converge. Now, this is very convenient to characterize equilibria, but it also means that we lose this information from initial state and how those affect equilibrium payoffs. So we lose the correspondence from the initial state to equilibrium payoffs, and we only get one limit equilibrium payoff set. Moreover, because we only look at the limit, we can't make any statements about the evolution of the game before convergence occurs. Then a second type of stochastic games that have been studied are absorbing games, where each state except a single state are absorbing. And these games we can, because the absorbing states are essentially a repeated game, we can first solve the continuation game in each absorbing state using the techniques that we know from repeated games. And then knowing what the continuation equilibria are, we can then use enforceability constraints to solve equilibria in the entire game. Of course, there are many other stochastic games that are not irreducible nor absorbing. And currently, we don't have a framework to somehow tackle all of them at once. And this is where continuous time methods will come in. When Sannikov first introduced continuous time repeated games, he showed that it is possible to characterize the set of perfect public equilibrium payoffs through a differential equation that describes its boundary for any level of patience, so for any level of discounting. Now, what that means is that we don't need to look at the limit as players get arbitrarily patient. And my idea was, well, if we apply this to stochastic games, then we could make a statement about the correspondence from initial state to equilibrium payoffs, because we don't need convergence to a steady state distribution. And this is the motivation of this paper here. We want to characterize the correspondence from initial states to perfect public equilibrium payoffs. And it turns out that we don't need to make too many assumptions about the underlying state process. One assumption that we do need is a full support monitoring assumption about the information that is revealed to players about past play. And I'll say a little bit more about this later on. Now, in a repeated game, we can characterize the boundary of the equilibrium payoff set through an ordinary differential equation. In a stochastic game, what we get is a set of coupled ODEs that describe the boundaries of the equilibrium payoff sets. Now, to solve these coupled ODEs is a little bit difficult. So what I show in this paper is that they can be approximated through a sequence of uncoupled ODEs. And then in the limit, as we look at the limiting ODE, similarly as in Sannikov, we can then recover the unique equilibrium action profiles that have to be played at the boundary on each of these sets. And so this way we can elicit the equilibrium profiles as well. Then related literature, a lot is related, essentially anything in repeated or stochastic games. So let me just point out the few papers that are most directly related. So the first one is by Herner, Sugaya, Takahashi, and Riei, who characterized the limit equilibrium payoff set in discrete-time stochastic games with imperfect public monitoring. And indeed, their argument does rely on the convergence to a steady state distribution, so it applies only to games in which the limit equilibrium payoff set is independent of the initial state. Then, of course, very much related is the paper by Sannikov that introduced all these continuous time techniques. Then my job market paper, where I extended the techniques in Sannikov to also account for discontinuous information arrival, such as the state process in continuous time stochastic games. And then I should mention, I guess, the paper by Neyman on continuous time stochastic games. So in that paper, he looks at games with perfect monitoring. And so the techniques will be quite different from the techniques in this paper. Good. Let's delve into the model. So the stochastic games that we consider are two-player games, and they're played continuously in time. With Y here will indicate the different possible states that the game can be in. And so it encodes the stage game that the players are playing. So we'll assume that the set of stage games that they can play is finite, and that each of these stage games is also relatively simple in the sense that each player only has finitely many pure actions available. Then by G of Y, we denote the ex ante expected payoff in stage game Y. And in the scope of the stochastic game, this will be interpreted as the expected flow payoff that players receive if they play action profile A in state Y. Time is continuous, so AT will indicate the chosen action profile at time t, and the state process is denoted by S, and it is a time homogeneous Markov process with instantaneous intensity lambda. So here it is important that this state process is time homogeneous so that the transition intensity from state to state does not depend on time itself, nor on the history of actions that have been played so far. So it is allowed to depend only on the current state, the continuation state, as well as the action profile that is chosen exactly at that time. And so we do need that so that we can recover a recursive structure of the game. And the assumption that I need is the full support assumption here, which says that if state Y prime can be reached from state Y after some action profile A has been played, then it is also possible to reach state Y prime after any other action profile has been played in that state. So this does not mean that all states can be reached from all other states, but it means that the set of states that can be reached from one state does not depend on the actions that are chosen. Or put differently, it's a full support assumption that ensures that players don't learn anything with certainty just by observing a state process. Now, the player's actions will not be observable. Instead, they observe the state process as well as a Brownian public signal. So the drift rate of the public signal depends on the chosen actions as well as the current state, but it can only be observed noisily because we'll add Brownian noise to that signal. And so all the information that the players have available is the history of the state process, the history of the public signal, and we assume that players have access to a public randomization device. So this will be useful because it ensures early on that the equilibrium payoff set is convex. And once we have convexity, we can analyze the boundary more simply. And then at the end, we can find out some certain conditions under which the equilibrium payoff set without public randomization is the same as the equilibrium payoff set with public randomization. And a strategy in this setting is then simply a predictable stochastic process that is predictable with respect to the public information. So this simply means can only depend on past evolution of state and public signal. And we will restrict attention to public strategies and pure strategies. Players discount their future utility using a common discount rate R, and they try to maximize their total discounted expected future payoff, or also known as continuation value. And so here, from all the future times between now and infinity, players look at the expected utility that they will get given the information that they have at time t. And this A here in the subscript of the expectation operator indicates that the players do take into account how their actions affects the distribution or the future distribution of the state process. So how their actions affect future opportunities. Then we use exponential discounting and we normalize so that the sum of all the weights integrates to 1. Now, since the weights integrate to 1, the continuation value is always a convex combination of stage game payoffs. So the set of feasible payoffs of the stochastic game is given by the convex hull of the union of all possible stage game payoffs. Now, when we discuss repeated or stochastic games, we often consider a lower bound on equilibrium payoffs that is given by the min-max payoff. And so in each state Y, the lowest possible enforceable payoff that players can get is the min-max payoff in that state. And so definitely a lower bound for the entire stochastic game if we minimize over all possible states. So this is the worst possible payoff that a player can get. And it's possible to get a tighter lower bound by taking into account how actions will affect state transitions, but this sort of primitive lower bound will be enough for what we do today. And we'll denote the set of all feasible payoffs that dominate this lower bound using the star. The main object of study will be the family of perfect public equilibrium payoff sets. And it is important here that we want to describe those for all possible initial states. Then in stochastic games, we are often also interested not just in perfect public equilibria, but also in simpler equilibria that are easier to implement perhaps, such as stationary Markov equilibria. A perfect public equilibrium is stationary Markov if it depends on the current history only through, if it depends on the entire history only through the current state. And so we can write it as a function from state to the available action profiles. And then if the states are non-redundant, then these are the same as Markov perfect equilibria. Then the techniques in this model will also give rise to a class of equilibria that are somehow between stationary Markov equilibria and perfect public equilibria. And I call those semi-stationary equilibria, where players take into account not only the current state, but the entire sequence of states that has been reached up to time t. Now, this is much less information than if the players observed the entire state process. So as an example, if we have, let's say, an irreducible stochastic game with two states, then we know what the sequence of state transition is going to be. It's always going to alternate between the two states, but we don't know when those will happen. And so in a sense, a semi-stationary equilibria is deterministic except for the times at which the state transitions occur. And we'll denote the associated payoff sets by EM for Markov and ES for semi-stationary. And we'll get this natural inclusion of equilibrium payoffs.
Can I ask a quick question?
Yes.
So can I view this semi-stationary equilibria as the limit where this Brownian noise is very high?
I suppose, or it's just not informative at all. Either interpretation works.
Okay.
Okay. Then let's look at an example of a regime change game. So we have two groups of different ideologies who compete for power. We'll have two states, where state yi indicates that group I is currently in charge. Then to make the example as simple as possible, we'll assume that each party has exactly two actions available. The group in charge can either work on policy reforms, which will have a positive impact on welfare, or it can manipulate the media in order to stay in power longer. Then the group that is currently in the opposition can choose to either accommodate that the other party is currently in charge and sort of live a quiet, productive life, or they can try to instigate a revolution to speed up the state transition and obtain power that way. Now, for the example that for the numbers that I will use, the state transitions are much higher if the opposition tries to instigate a revolution than if they do not. And we assume that by manipulating the media, the party in power can essentially cut down the frequency of revolutions by half. Then the public signal that we use in this example, so we assume that actions are not directly observable. If the opposition tries to instigate a revolution, it will not be public about it, and the government will not publicly announce that they control the media. But so the information that the players will receive is sort of a two-dimensional welfare, or sort of a two-dimensional welfare measure. So the first dimension will capture improvement of welfare that is enjoyed by both or by groups of both ideologies. And then the second one will capture policy changes on which the two groups disagree. So we can think of this as maybe an orthogonal decomposition of welfare into one axis that they both enjoy and one that they are completely opposed to each other. And yeah, if both choose the productive action, then the first component of welfare will improve much more than if only one of them tries to improve welfare. And we assume that if the opposing party tries to instigate a revolution, then the policy changes where they disagree will be stronger because somehow the party in charge will be more oppressive as a response. And the payoffs that the parties receive. So the first component is enjoyed by both parties. And here the second party enjoys positive changes in the second component, and the first party enjoys negative changes in the second component. And then there will be a cost to the cooperative action profiles. And if we take the expectation of this payoff stream and look what the ex-ante flow payoff is, then we obtain the stage game payoffs, and we simply take the expectation of these two processes. And so here, the state changes affect the utilities through the state in which the players are in. Then if we look at the graph of these stage game payoffs, then, so here the two axes are the two groups payoffs, and we see all the pure action stage game payoffs, as well as the set of feasible and individually rational payoffs. So in this case, the min-max payoff in both states is 0. And so this is actually the feasible and individually rational payoffs in both states. Good. Any questions so far? Good. Then let's think about how we can construct equilibria in this model. Now, the first thing to construct equilibria, if we have imperfect public monitoring, we need to know sort of what information the two parties, or in general, the players observe, and then how the information affects the player's continuation value. So there's two types of information that they see. They observe the frequency of state transitions. And so here we'll introduce some additional notation. JY will be the counting process that counts how many state transitions have occurred from any state to state Y. And so we'll have one such counting process for all states. And they observe the public signal, which will look something like this. Now, what players would really like to know is the underlying frequency of state changes or the drift rate of the public signal, because those are what depends on the opponent's action profiles. And the expected change in the continuation value, not the expected change in the public signal, will determine the expected change in the continuation value. And so what we can use to provide incentives is how much the observed signal deviates from the expected change. So these two, I suppose, would be martingales, are what we can use to provide incentives. So specifically, one can show that the continuation value satisfies the following stochastic differential equation. It has 4 terms, and we do see here these deviations from the observed signal to the expected signal, as well as the observed states to the expected state changes. So the first term will indicate the expected change of the continuation value. And we see that it points away from the expected flow payoff. So if a player currently receives a higher flow payoff than their expected continuation value, then it has to decrease the continuation value and expectation because they are over-consuming. And similarly, if the current ex-ante flow payoff is lower than the continuation value, then it has to increase in expectation. Then we have the sensitivity to the public signal, where beta I here captures the sensitivity. Then delta I, Y, captures the sensitivity to state transition to state Y. And so we will be able to use beta here and delta to provide incentives. So let's say if delta is large for some Y, then this means that a party will be rewarded by a higher continuation value if the state changes to Y. And then lastly, we have a martingale M that arises because players can use public randomization. And as I've mentioned, public randomization is needed only for making sure that the equilibrium payoff sets are convex. After that, we won't need it anymore. So for the rest of the presentation, you won't be seeing M anymore. Let me see. Hang up the phone. I apologize. Good. Now, so we can use beta and delta to provide incentives. And what we're trying to ensure, if we try to enforce a certain strategy profile, then we want to make sure that the player's expected flow payoff and the sum of the expected changes due to the public signal, as well as state transition, is maximized over all unilateral deviations. And so if this enforceability condition is satisfied, then no player will have an incentive to deviate. Because even though maybe the current flow payoff would be higher, if they take into account how it will affect future opportunities, they know it's not worth changing the chosen action profile. And so here we'll use lambda YA to denote the vector of all intensities of all state changes away from Y. And so this way we can easily write down the sum of expected payoffs due to all the state changes as the scalar product from delta and lambda. And a strategy profile is a perfect public equilibrium if and only if at all points in time to the sensitivities here to the public signal enforce the chosen action profile. Yeah, so these, yeah, in a sense, if the continuation promise is kept, then nobody has an incentive to deviate. So that is a continuous time equivalent to the one-shot deviation principle. Now, these two slides give us an idea how we want to construct equilibria in continuous time as an enforceable solution to this stochastic differential equation. Now, and this gives us an idea that we could perhaps construct the boundaries of the equilibrium payoff sets by using stochastic control to ensure that the continuation value of a PPE remains in the equilibrium payoff set at all times. So we know by public perfection that at any time t, the continuation value will be in the equilibrium payoff set with initial state as t. And so we will want to use stochastic control to make sure that the solution to the STE somehow remains within the set. The fundamental problem, both in discrete time and in continuous time, is that we don't know a priori where this boundary lies. Now, in discrete time, we use self-generation to solve this problem. We characterize the equilibrium payoff set as the largest self-generating set, and then it's enough to find any self-generating set to find equilibrium payoffs. And this approach we will pursue here as well in continuous time. A self-generating payoff set or a family of self-generating payoff sets in continuous time is a family of payoffs, W, one for each state, such that any payoff within any one of these sets can be attained by an enforceable solution to this STE that remains within the family of payoff sets at all times. So in essence, if we can somehow find an enforceable strategy profile whose continuation value remains within the set forever, and then we find this is a self-generating payoff set. Now, if we have a self-generating payoff set, this tells us something about the incentives that we can provide on the boundary of these equilibrium payoff sets. So if we have a point W here on the boundary, then because the continuation value of an equilibrium has to remain within this set, we know that the drift rate certainly has to point towards the interior of the set. And so if we write it down in game primitives, this means that this scalar product here is non-negative. Then the public signal that we use to provide incentives, because Brownian motion has unbounded oscillation, because it oscillates infinitely quickly, we have to provide incentives through the public signal. We have to use those as value transfers. If we use it in any other direction, then because of infinite variation, it would escape the equilibrium payoff set immediately. And so as a result, the public signal, because it is Brownian, can be used only to provide tangential value transfers between players. And then lastly, incentives from state changes, they simply have to come from the right continuation set. And so if R delta is the size of the jump, then W plus R delta has to be within the appropriate continuation equilibrium payoff set at all times. Now let me on one slide try to explain what the difference is between the equilibrium characterization in repeated games and stochastic games. Now in repeated games, there are no state changes. And as a consequence, we only have the public signal to provide incentives. And also in repeated games, those have to be provided tangentially to the equilibrium payoff set. Now what Sannikov showed is that we can characterize the boundary of the equilibrium payoff set through an ODE that depends on the unique equilibrium incentives that can be provided at that point. And because the signal is Brownian, the space of available incentives is equal to the tangent space at this point. So specifically, this means that it depends on the geometry of the equilibrium payoff set only through local information, only through the direction of the tangent. So this means if we can write down a differential equation that involves the state, the first derivative, which is the normal vector, the second derivative, the curvature, as well as the space of available incentives, then we do get a second order ODE because the space of available incentives itself depends only on the first derivative as well as the state. Now, if we look at stochastic games, this is no longer true. The set of available incentives now depends not only on the direction of the tangent, but it depends on all the other equilibrium payoff sets as well. So if we want to characterize a point on the boundary through an ODE about the optimal incentives, then necessarily we'll get a set of coupled ODEs where the incentives at one point depend on the solutions of the ODEs in the other states. Now, the first thing that we'll have to deal with is we'll want to decouple these ODEs so that we can solve them in an easier way. Sort of a naive way to decouple these ODEs is to say, well, what happens if we just fix all the payoff sets except one? So we just think that we have found them already somehow, and then we'll try to characterize the last one. Then what are we trying to do? We're essentially trying to find the largest self-generating set that is self-generating up until the first state transition. And then we know that from that point on, the continuation value will lie in some fixed sets that we choose. And because those sets are fixed, now the set of available incentives depends only on the direction of the tangent and some constant that we have chosen. And so in the scope of the entire stochastic game, we will refer to such a set as relaxed self-generating because we have relaxed the condition and look only at one set at a time. So such a set is a payoff set so that any payoff within that set can be attained by a locally enforceable solution, so by locally an enforceable strategy profile that remains within this set up until the first state transition, and then it jumps to the target sets that we have chosen. And so these games are essentially, these auxiliary games that we consider are essentially a repeated game with random termination. Now, what do we obtain if we find the largest relaxed self-generating set? We don't get the equilibrium payoff set unless we have chosen set for all the other states correctly somehow. But in general, what we do obtain is the equilibrium payoff set of these auxiliary games. And the reason why those will be useful is because we can use them to concatenate the solutions to this SD, so we can concatenate those strategy profiles at the transition times of the state transition. So in a sense, we construct locally an equilibrium while the state is fixed until the next state transition occurs, and then we try to concatenate it at that point with the auxiliary game from the next state. So let me illustrate this with a figure. So we have some family of payoff sets, one for each state, that we have fixed somehow. And then we look at all the other payoff sets fixed except those in state one, and then we try to find the largest self-generating set up until the first state transition. Then, okay, we can find some set, and then the continuation value after state transition will lie in one of these sets. And so let's say the state transitions to state Y2. Then this is particularly useful if we can again attain those payoffs by another solution until the next state transition. So if the largest relaxed self-generating payoff set in state 2 contains WY2. Then if this is true for all the states, then we can concatenate the solution after every state transition, and then we get a global solution. So if W is contained within this B of W for all states Y, then we have found a family of self-generating payoff sets. Conversely, if W is self-generating, then this inclusion has to hold for all states. Now, if you think that this looks very similar to the APS operator, then you're absolutely correct. This is sort of a continuous time stochastic game analog to the APS operator. And if we apply it iteratively to our payoff bound V star, then it will converge to the equilibrium or to the family of equilibrium payoffs. Good. The hard part is over. And now we have to characterize the boundary of each of these sets B of W when all the other payoff sets are fixed. And this can be interpreted quite nicely using some figures. So there will be 4 types of boundary payoffs that we have to deal with. The first one are those payoffs where incentives through the public signal are needed. So it is not possible to provide incentives only through the state transitions. Now at those points, because the public signal is used, the boundary has to be smooth. Because we use these Brownian signals, it's not possible that there's a corner at any such point. And so at all these points, we obtain a second order ODE similar to Sannikov. Then what happens if incentives from the public signal are not needed? Well, in that case, the boundary doesn't have to be smooth. All that is left is the drift, as well as the continuation to the other payoff sets. And so in that case, we'll get 3 different types of boundary states that we'll characterize one by one. So let me start first with the points on the boundary where incentives from the public signal are needed. And those will determine some additional assumptions that we need on the distribution of the public signal. So let me give you a 2-slide summary of this procedure that was developed by Sannikov. So let's abstract away from the entire goal of trying to characterize this largest relaxed self-generating set. Let's try to think of how can we ensure that the continuation value of an enforceable strategy profile remains on a specific curve C. Now, because we use the public signal to provide incentives, and those oscillate very quickly, the infinite tangential oscillation will lead to a drift away from the curve. So this is something like the centrifugal force in physics. The faster it oscillates, the further we go away from the center of the curve. And the outward drift will be stronger the larger the curvature is, similarly as the centrifugal force is stronger the smaller the radius of the centrifuge is. Now, the precise amount of the outward drift can be characterized by Ero's formula, and we see that indeed it is proportional to the curvature. Now, if this continuation value stays on the curve, then this outward drift has to be precisely counteracted by the inward drift. And so we get an equation that we can solve for the curvature. And so this will give us the second order ODE that has to be satisfied at any point on the boundary where incentives from the public signal are needed. Now, so this term here is the solution to the equation on the previous slide. And in order to get the curvature, we have to take the maximum over all enforceable action profiles, as well as all incentives that enforce that action profile. The reason why we have to take the maximum is that if this was not the maximum, then we could find a solution C to this ODE, and it would have to fall into the interior of this set B. If it falls into the interior, then we can change initial conditions slightly so that the curve leaves the set B and comes back. Now, with the construction on the previous slide, we can attain any payoff on this curve with an enforceable strategy profile that remains on the curve. And so we can attain any payoff outside B up until the next state transition. And so this would be a contradiction to the fact that B is the largest relaxed self-generating payoff set. Now, what this does require is it does require that this ODE is continuous in initial conditions. So we will have to make an assumption that ensures local Lipschitz continuity of this ODE. And I'll mention this assumption once we get to the main result. Good. So we have characterized the first type of boundary points. And now let's look at the other three. So if the public signal is not needed to provide incentives, then the simplest way that we could provide incentives is if this expression here, G plus delta lambda, if this were exactly equal to W. In that case, there would be no drift. And so the continuation value would remain locally constant at W until it jumps to the correct target set once a state transition occurs. And so then this point here is self-generating or locally self-generating by itself because the continuation value just remains there until a state transition occurs. And so we call those points stationary payoffs. So formally, we'll introduce some notation. Psi will indicate the set of all rewards or punishment after state transition delta that enforce A. Then if we add the W's, then it simply means that if a state transition occurs, the continuation value will jump to W. And if the argument includes N as well, then we also require inward drift. So for stationary payoffs, inward drift wasn't necessary because the drift is 0. And so we get the set of all stationary payoffs as the set of all those payoffs that can be decomposed into current period payoff and expected change from state transitions. And as mentioned on the previous slide, all of those are relaxed self-generating, so all of those are contained in B. Let's go back to the example and let's see how the set of stationary payoffs looks like in this example. So let's see how we can provide incentives for the cooperative action profile PA. So in order for player 1 to work on policies instead of manipulating the media, it is necessary that a state transition is not too costly. If a state transition was too costly, then player 1 would have an incentive to deviate and try to reduce the frequency of state transitions. So we'll get a lower bound on how a state transition can affect player 1's continuation value. Then for player 2, in order for player 2 to play the cooperative action, it must be that a state change is not too profitable. If it was too profitable, they would have an incentive to speed up the state transition. And so relevant for the construction of the stationary payoffs will be this bound here, that player 2 cannot be rewarded too much. So specifically, the continuation value after state transition has to lie in this target set V star. And this is using stationary or stationarity, we can decompose W into the current stage game payoffs as well as the expected change in continuation payoff, and then we have the state transition. So we can now use the set of all delta and enforce A that we have computed on the previous slide. And if we scale it by a factor of lambda plus R, and we add the stage game payoffs, then we'll get all continuation payoffs that can be attained from a stationary payoff. And so on the previous slide, we have deduced that as long as player 2 is not rewarded too much. And so we see that this will now be everything below here, starting from G when player 2 is not rewarded too much. So we take the intersection with our target set, V star, and then we almost have found the set of stationary payoffs. What we have found is now G plus delta times lambda plus R, and we only want G plus delta lambda. So we rescale this set back to G using this factor here. And so these will be all the stationary payoffs in that state for this action profile. And we can do the same construction for all other action profiles, and it turns out that this will be the stationary payoffs. And the reason why this has such a nice visual interpretation is because in this case, there's only one state that can be reached. And so the intensities of states that can be reached is one-dimensional. So this gives us a nice decomposition in the payoff space. Now, if there are more than one future state, then we do the same operation in the incentive space rather than in the payoff space, but the same procedure will work. Okay, 2 down, 2 to go. For the last type of boundary payoffs, well, if the continuation value is not stationary, then it will move deterministically until it transitions to another state. And there's 2 possible cases. It could either be tangential or it could fall into the interior of W. And to distinguish between the 2, we have a relatively intuitive impossibility result, which says that at the boundary, at least one of the conditions has to be binding. It's not possible that incentives are provided strictly and the drift points strictly into the interior, because if it was, then we could just change the rewards a little bit and attain a payoff outside B of W. So let's suppose now first that the first condition holds, that incentives are provided strictly. In that case, the drift has to be tangential to the equilibrium payoff set. And it has to be tangential in the direction of all outward normal vectors. So this is particularly interesting when there is more than one outward normal vector. So if G plus delta lambda lies on the tangent through W, or on both tangent, then it has to be exactly equal to W. So those are precisely the stationary points that we have already characterized. So this means that all the points that are left to characterize, if incentives are provided strictly, then the boundary is smooth and the drift is parallel. Lastly, if the drift points strictly into the interior, then incentives have to bind and they have to be extremal from this set W. So as a summary, if the first condition holds, we get a first order ODE, which I will call the parallel drift ODE. And then if the second condition holds instead, then incentives have to be binding an extremal in W, and we'll denote those points by K. And again, we want to know how does that look like in our example. So in order to provide incentives for sort of the uncooperative action profile, turns out the player 1 cannot be, or has to be punished by at least this amount, and player 2 cannot be punished too much. Now, where are incentives binding and extremal in V star? Well, for player 2, it's anywhere on this line, because from that way, from these points, we can directly reach the extremal point in V star, at which player 2 is punished by exactly 1/2. For player 1, those are exactly these points. And now we can't attain payoffs up here because it would not be possible to provide incentives to both players. So instead, we get all these payoffs here are payoffs where incentives bind and are extremal for at least one player. Another way how we can construct this is we translate the target set by these extremal incentives that have to be provided, and then we look at an infinite extension of it based on in which direction these inequalities go. And again, if there are more than one continuation state, then we do the same operation in the incentive space rather than in the payoff space. So these are all the points. I'll show the picture of how the entire set looks like after the statement of the main result. So it looks relatively complicated because there are these four conditions that we have to distinguish. So we denote by gamma here the set of all payoff direction pairs where incentives from the public signal are needed. And then we can characterize B of W as the largest closed convex set that contains all the stationary payoffs and has these two properties. So all the corners of this set are either stationary or lie on this payoff set K. And outside of those payoffs, outside of those corners, the boundary is continuously differentiable. And within gamma, it's a solution to the second order ODE. And outside of gamma, it's a solution to the first order ODE. Now, here we do need to make assumptions such that the curvature is locally Lipschitz continuous. And a sufficient condition that I have currently is that the continuous signal satisfies a pairwise full rank condition. So this means that deviations by the two players can be statistically distinguished, and that for any rewards or punishments upon a state transition, there exists some value transfers that enforce the action profile. Now, these conditions can be relaxed. We don't need that all action profiles are enforceable. And there's some other ways how we can relax it for a specific game. But so in general, this is a sufficient condition for which the result will hold. And the set B of V star will look like this in our example of the regime change game. So we see the stationary payoff sets that we have characterized before, and we see this set K, the only payoffs where we can have corners of this set B of W. And everywhere outside the stationary payoffs and these and this gray line here, the boundary is smooth. So on this part of the boundary, it is a solution to the second order ODE, and on the other parts of the boundary, it's a solution to the first order ODE, and the continuation value will drift upwards or towards this point here, and here will move towards the bottom. And then lastly, we have one boundary payoff where the drift goes to the interior of the payoff set. Now, because the game is symmetric, there are two states, and for each state, I will get one set in this family. And so these are the sets that we obtain after one application of B. And if we apply this operator several times, then eventually it will converge to the family of equilibrium payoffs. And so now in the limit, those satisfy the coupled ODEs that we have talked about. Good. In the last few minutes, let me say something about the stationary or semi-stationary equilibria. So if in each state, we just compute the set of stationary payoffs and then see where the payoff set converges to, if we just keep applying S, then it will converge to the set of stationary Markov equilibria. So we see here that these 4 points will remain, corresponding to 2 different stationary Markov equilibria. If in each step of the iteration, we also take the convex hull of the stationary payoffs, then more will survive. And what we will get is the set of semi-stationary equilibrium payoffs. How can we understand the stationary Markov and the semi-stationary equilibria in the example that we looked at? So the stationary Markov equilibria, there are 2 of them. And the continuation value just jumps back and forth when the state changes. And we see that the stationary Markov equilibrium supports the cooperative action in one state, but not in the other. So we see that one party will always choose to instigate a revolution if they are not in charge. Then the semi-stationary equilibrium, let's see how we can attain this most efficient payoff W star. So locally, the continuation value is constant until a state change occurs and will point away from the current period payoff and attain some point in the other semi-stationary payoff set. Then after 4 state changes, after 4 regime changes, we'll end up at this point here where we can no longer provide incentives from this payoff set here. And so here we use public randomization to be absorbed in one of the stationary Markov equilibria. And we see how we can improve efficiency by sort of delaying the destructive action for 4 periods. So we say, okay, the first 4 times that a regime change occurs, we will play the cooperative action profile, and only afterwards we'll switch to this stationary behavior where one party always chooses to instigate a revolution. Good. Let me conclude. So in this paper, what we're achieving is that we're able to characterize the set of PPE payoffs through a sequence of convergent ODEs. And this works for any discount rate. And it gives us a correspondence from initial state to equilibrium payoffs. So we can recover at the end what the impact of the initial state is. Then, in addition to the PPE, I also characterize stationary Markov equilibria as well as semi-stationary that sort of arise as using a smaller set in each state of the algorithm. Then what is new compared to discrete time? Well, the fact that we have the correspondence from initial state to equilibrium payoffs and that we need fewer assumptions on the state process. So it's applicable to a wider class of stochastic games. The drawback is that it needs relatively strong assumptions on the distribution of the public signal. So we need here, our sufficient condition is that it satisfies a pairwise full rank condition. So I guess you can't have everything. Good. That's the end. Thanks for having me and thanks for listening to my talk.
So before going to questions, please let me join you and thank Ben for this talk.
Thank you.
So let me stop the recording.